Hello and welcome to Lecture 2 in the unit on Gauss's law in PHYS 1204. And in the last lecture we actually met the idea of electric flux, but I haven't called it electric flux yet. So this lecture is all about lecture flux, and so we'll start off by talking about what a flux is. We're going to be interested in electrical flux, but the idea of a flux is very general, and so we might as well start by talking about something a little more intuitive. So here is a marching band going down a street, and they're a well-trained marching band, so they're all walking with the same velocity v. Let's think about them passing by this line A, except I don't want you to think of this as a line. I want you to think of this as an area, a surface that they're walking through. So perhaps it's one of those inflatable archways being used as the end point of the parade. And we want to know how many musicians per unit time walk through the archway, pass through the surface. In particular, we want to know what affects that. So, for example, if the marching band walks at twice the speed, we know that twice as many of them are going to pass through the archway per unit time. And so that means that this thing, the number of musicians per unit time passing through the surface, which is what we would call the musician flux, phi sub m, must be proportional to the speed that they walk at. Notice there's no vector symbol here. It's not in bold. That is a speed, not a velocity. Similarly, we could double the width of the road and double the width of the archway. So now we've doubled the area of the surface that they're marching through. And that ought to also double the number of musicians marching through the surface per unit time. And so the musician flux must be proportional to both the speed that the musicians march at and the area of the surface that they're marching through. Let's talk about another flux, but it's the same idea. Here is a floor plan of a building and velocity vectors for air currents moving around inside it. And perhaps an engineer working on the ventilation system for the building might be interested in how much air per unit time passes through this doorway here. So we would define the area of the doorway, and if all of the air going through it is at one speed, we could find the speed times that area of the doorway. And if you just think about the units of that, that has units of cubic meters per second, which is a volume per unit time. So this air flux, just the speed times the area of the doorway, has the desired meaning. It is a volume per unit time of air. In the examples we've been looking at so far, the vectors we've been concerned with are velocity vectors. And if you want to, because it's intuitive, you can keep thinking of these as velocity vectors. But at this point, I'm just going to say these are some general vector v. And also in the examples we've been looking at, these vectors have always been perpendicular to the surface that we're thinking about them passing through. And so the flux ends up just being the speed, or the magnitude of these vectors, times that area. But that won't always be the case, because sometimes your area will not be perpendicular to the vectors. So the other extreme is when the vectors are going tangent to the area. Now none of them pass through that area, and the flux is zero. But more generally, they may be at some other angle. So then how do you calculate the flux? Now I will say, in this unit we will almost always arrange for our vectors, electric field vectors in this case, to either be perpendicular to or tangent to the surfaces that we're thinking about. But we should think about how to do it more generally. So if you look at the geometry here, you can see that with this definition of the angle, we can define a different area here so that a perpendicular to it comes over to the top of the surface of the area that we're actually thinking about. And so now, if h is this length of the area we actually want to know about, then this side here is h cos theta. And their widths this way are the same, and so that tells you that the area of this piece is just A cos theta, where A is the original area we wanted. And the flux through this surface must be the same as the flux through this surface, and so we see the flux must just have this cosine dependence on this angle. This is already a pretty abstract quantity, this flux phi, although for things like airflow it isn't so abstract. However, there's another way we can write it, which makes it often easier to calculate at the cost of some further abstraction. So what we do is we define a funny vector. We'll call it A here. It is a vector which is perpendicular to the surface and has a magnitude equal to the area of the surface. That's a rather curious vector. And it may be easier to picture that in a straight-on side view like so, which makes it clear that the angle that the area is making with our perpendicular is the same as the angle that our new vector A is making to the vectors going through the area. And we're familiar with this sort of setup where we have an A vector and a V vector separated by an angle theta, and we want VA cos theta. That's just the dot product. And so that is often how we will write fluxes. Now it's time to define the actual quantity we're interested in at the moment, which is the electric flux. And we've already done all the work towards being able to define it. We just have to substitute in the E field for the more general vectors that we've been thinking about. So it is just the dot product of the E field pointing through a surface with an area vector perpendicular to the surface and proportional to the area of the surface. And so this is mathematically the same as the fluxes we've been looking at. However, be very, very careful. The fluxes we've been looking at to develop an intuition for this talked about physical flows of stuff, air or musicians, through a surface. The electric field is not a flow of stuff. There's nothing moving here. And so the electric flux doesn't refer to anything physical flowing through the surface. It's in some sense how much field pokes through the surface, perhaps. And the other caution is that this formula here only applies to flat surfaces and uniform fields. As soon as we move away from flat surfaces and uniform fields, we would have to turn this into an integral, which we'll see. Here's a quick example, both to demonstrate some of these new ideas and also to remind you of some old ones. So here's a parallel plate capacitor, and I've told you the charges, and I've told you the dimensions. Note the diagram isn't to scale. And here's a surface, and we're going to stick this surface in here and calculate the flux through it. But before we do that, let me just remind you, if we can ignore edge effects, then the E field in here is uniform. It's the same no matter where we look. And so what that means is that when we take this surface and put it in here, we can snug it up against this plate, or we can snug it up against this plate, or put it anywhere in between, and we're going to get the same flux. So I'm just going to drop it down any old place and remind you that we're going to get the flux, the electric flux, by E dot A. And let's just look at that area vector. That area vector is perpendicular to the surface and has a magnitude equal to the area of the surface. Well, that means it's parallel to the E field. And so E dot A is just going to be EA cos theta, but theta is 0, and we know that cos of 0 is 1. And so we just get E times A. Well, we don't know E, but we can get it easily because this is a parallel plate capacitor, and so that's just eta over epsilon naught. And eta is just the charge on one of the plates over the area of the plates, so this ends up being Q over epsilon naught A once we put that in. And so we're almost done. Our phi sub E, our flux, is just the electric field times the area. Note that the area of the surface is the same as the area of the plates. That's why I'm calling them both A. And so those just cancel, and we get a very nice, simple Q over epsilon naught. So that's 2 times 10 to the negative 8 coulombs, right? That's the charge on one of the plates, over 8.85 times 10 to the negative 12, and careful of the units, coulombs squared per Newton meter squared. Well, you can plug that into your calculator as well as I can. I really don't care about the number. It's around about 10 to the 3. And look at the units. That's what I do want to pay some attention to. It comes out Newton meter squared per coulomb. It had to, right? Because that is an E field in newtons per coulomb times an area in meters squared. I will point out that there are some other ways that these can crop up when you calculate in different ways. Sometimes you see this come out differently, and it's nice to realize that these other forms are fluxes. Newton meters is joules, so you could turn this into joule meters per coulomb, and a joule per coulomb is a volt, so volt meters. So these are all different ways that fluxes come out, but we'll normally write it this way as Newton meter squared per coulomb. One last thing, this quantity probably isn't very meaningful to you, and that's because, in fact, it really isn't very meaningful. We don't really calculate fluxes for their own sake. As you'll see in the next unit, in the next lecture, when we look at Gauss's law, we use the flux to get E fields. E fields are our target here. Finish up, I just want to talk a little bit about something we won't do much of. We may look at it in class, and I may put a simple example of it on the assignment. But that's to calculate a flux when you have a curved surface and or a non-uniform E field. And so I've tried to draw a curved surface here. That's sort of hard to draw, and suggest an E field going through it, which is varying with location. And let's just think about how you would calculate the flux through here. And you may have a sense that whenever we have these sorts of cases with continuously varying quantities, it's going to result in an integral. And this is no exception. So we're going to be able to define some little areas, right? Break up the surface into little areas, like so. And then we can define little bits of area vector. So this delta A vector is perpendicular to this piece of the surface and and has a magnitude equal to its size. And so our total flux through the surface would now be approximately a sum of E field vectors through little bits dotted with those delta A's. And so that means the exact one is going to be an integral. This is an integral over the surface of E dot dA, where these dA's are infinitesimal area vectors. And that probably looks pretty scary because you don't know how to do an integral over a surface, but we'll in fact see simple examples of it in the next lecture.